Hey there, I'm srcmake and welcome to the video on the trie data structure. In this video, we are going to talk about what a trie is, and I've got this diagram here that we're going to go through so it makes some sense. Then we are going to talk about the underlying data model behind how you would construct a trie. So trie is an advanced data structure, so we have to build it up from something. This section is going to talk about that, and we've got a few choices to make, so that'll be super important. Then we have a section on the operations that we can perform on a trie. So once we've got this trie sort of set up, we need to actually be able to interact with it, and that's what we are going to do with this section. There are two important operations that we are going to go through. One is insert and one is contains. So I've got some pseudocode written here that we are going to go over at a high level, and then I'm going to go through some examples and draw them out in Microsoft Paint so we see how everything actually works out. And so that'll be really helpful in understanding how tries actually work. And I've also got some full C++ code. So this is pseudocode right there that we're going to go through, but when it comes time to actually translate it to real code, I've got some C++ code that I wrote out that we are going to go through at a very high level. If you don't know C++, don't worry about it. We just want to see how we would actually write this out in some real object-oriented class structure. So that's what this section will be about. And finally, we will end the video by looking at when you would actually use a trie. Like, what are the best use cases, and when should you think, oh, this problem means we should use a trie? That's what this section is going to be about. And that's basically it for this video. So this blog post and the GitHub links will be below this video. You can click those links if you want to get to those pages. And while you're down there, hit the subscribe button to this YouTube channel. Thanks. So the trie data structure. So a trie is a tree data structure that stores sequences of anything. Could be sequences of numbers, characters, strings, any sort of sequence you want. Keep your mind open. A tree data structure that stores those sequences in a way such that overlapping elements that are in the same position can share the same node. So for example, if we got this trie right here, you can see that we've inserted the words ant, any, appl, apply, make, and source into this trie. And the reason that this trie is better than other data structures is because overlapping characters. So our nodes, each one of these holds a character. You can see the letter A is inside of this node. You can tell that this, for ant and any, they both share A at the first index of their strings. And so that's why a trie would be great for memory efficiency, because instead of writing each one of these having to have, like, be its own string and have the letter A at the first position, we can just share that node. And so this scales up really well if we have a lot of sequences that we have to store. Not only that, we'll see later on that when we want to perform certain operations like checking if a word exists in our dictionary that we've had so far, a trie is really useful and really quick to check that. It's even better than hash maps. So that's basically what a trie is at a high level. So a trie is implemented as a tree data structure, as you can see, and each one of the nodes of these trees holds three things. It holds the data that is part of the sequence. So in this example right here, we have pure uppercase English letters, and so each one of these nodes holds an uppercase English letter, which is going to be a character in our case. You can see this node holds A, this node holds N, this node holds M. That's the actual data. And then we've got a Boolean that says whether the node is the end of a sequence. So this one's a little tricky and it's not shown in this picture, but let's say we wanted to insert the word an, A-N, in our trie. Well, you can't tell that this is the end of a sequence by the normal method of seeing that it's a leaf node. So for example, if you look at ant, if you go down the tree, A and T, you could automatically assume that this is the end of a sequence, meaning that our total word so far is going to be ant because this is a leaf node, it has no children. But for the word an, you can't tell that because there are future nodes that do have, nodes, and so that would be continuations of the sequence. So what we need to do is we just need to have a Boolean in each one of these nodes that says, hey, this node is the end of a sequence, and that's how you know if the sequence is valid or not. So when we go through, we see A, N, we see that Boolean is true, and we're like, oh, okay, so far this is a valid sequence, and we can still continue to see, oh yeah, okay, ant is a valid sequence, and any is a valid sequence. So just keep that Boolean in mind. And then finally, a list of pointers to other nodes. So usually in like a binary tree, you would have left and right, but right here, you can see for this node right here, we've actually got 3 pointers. It's not just 2. And so depending on our trie, we might have many pointers, and we just need to know how many pointers. Each node is going to have to point to a certain number of other nodes based on what our trie is doing. That's what these green lines are. Just keep that in mind. That's what we're going to talk about in this next section. So moving on, the underlying data model behind a trie. As we just said, a trie is represented as a tree of nodes. And what we have to do ahead of time that we just alluded to is decide how many pointers to each trie node each node is going to have. We need to know, okay, our node, how many other pointers do we need? And for uppercase English letters, that would be like 26. So, for example, a trie that holds uppercase English letters might only need 26 pointers exactly. One for A, one for B, one for C, one all the way to Z. But maybe our trie holds phone numbers, and so we don't need 26. All we need is like 10. We're only going to have like 10 digits at most for each sequence, and so that's, 10 would be valid for us. We need to know that ahead of time. So now we have some choices to make. In our example that we're going to be going through today, we are going to hold basically characters, English letters. And so one thing we might do is we might say, this is what our trie node is going to look like. This is actually valid C++ code. We're going to have that character C to hold the letter. We're going to have this Boolean is end of sequence that we talked about before. And then maybe we could have 26 of these pointers to trie nodes. So we've got a variable named next node A, and that is going to be a pointer to a trie node, and that would point to the next A in the sequence if one existed. And we could have 26 of those, one for each uppercase English letter. So that's a little bit weird to have 26 of those. It might work for just left and right pointers for binary trees, but that's not going to work for a trie. So what we could do is we could just have an array of these pointers and have some index mapping. So in this example, we still have character and Boolean, but this time for our trie node, we have an array that holds 26 of those pointers. And so maybe the 0th index of next nodes maps to the A of the next node, and the 25th index would map to the Z. And so we could do some indexing tricks, and that would be a little more cleaner code to write. Now that's good, and that's actually pretty efficient if we know we're dealing with all uppercase English letters, but I want it to be a bit more flexible for our example, and to, be able to just be more flexible. So in this example that we're going to be doing today, I am using a hash map that maps a character to a trie node pointer, and that's going to be a variable named next nodes. So basically what our hash map is going to do is it's going to map a character, for example, A, capital A, or even lowercase a, and that's going to map to another trie node. It's going to hold a pointer. And that's just C++ syntax. Don't worry about it if you don't want to worry about the pointers. But now our nodes can point to arbitrarily many other nodes without having to know ahead of time. So for example, if a special character came up like an exclamation point or a question mark or the and symbol, we can just, handle that without needing to know that ahead of time, because we're using a hash map and we can, add as many valid characters as we want to ahead of time without declaring a specific number. That's basically what we're going to be doing. That's a flexible approach. It's less efficient because our hash map might have extra memory assigned instead of just like the exact 26 that we might need. But for our example, it's going to be super helpful and useful. So that's basically what our trie node is going to be constructed of. Each node of our trie is going to have a character, a Boolean, and a hash map that maps a character to another node. And in C++, it's going to be pointers, but don't worry about that detail if you don't want to. So now the operations that we can perform on a trie node. There's going to be 3 important things that we're going to go over. One of them is initializing the trie. One of them is going to be inserting a word into the trie. So we've got this trie set up, but we want to insert those words. And finally, we are going to look at this one cool operation, which is contains. So we want to check if we inserted a word or not inside the trie. Does the trie have this word inserted or not? Right now, a trie is basically going to be a dictionary. That's what you should think of it of. Not like a hash map, but like a trie. So that's the 3 operations. Let's draw this out to make sure it makes total sense to us. So the first operation is going to be initializing the trie. You can see all we're going to do is initialize a new trie node with no character. It's going to be empty. You can see in this example up here, all tries have an empty root, and that's basically what we need to do when we initialize a trie. So I'm just going to draw that out as an empty. Let's make that a bit thicker. That's going to be an empty circle. Super simple. So the next thing that we want to do is insert. So let's take 2 examples. We're going to insert, if you look at this function signature, it returns nothing, and you have to pass in a word. You need to tell the trie what words you want to insert. So we're going to insert the words any and an. Those are the two words we're going to insert. Let's look at this code really quickly. So it's a simple function. This is pseudocode, so don't get too into the details. Called insert, returns nothing, and you pass it in a string. There are two things that are going on here. There's two iterations, two loops, basically. One is going to be a try node that is going to be called current node that starts at the root that we are going to use to traverse the try, and then the other loop is going to be looping through each character in the word. We need to keep track of two things. We're going through two things at the same time, and that's basically how it works. So our initial current node is going to point to the root, and our for loop is going to go through each one of the characters at each time. So that's going to start at the character A in our word any. So this is basically what the code does. This is super simple. We are going to look from the current node to see if a node exists for the character, if there's a pointer to the next character, if that node exists. And if it does not exist, we are going to create it. If it does exist, we are just going to get a reference to that and update current node to point to that next node if it exists. We don't need to create it if it already exists. That's basically all that means. And then finally, for the insert, we need to worry about setting up that is_end of sequence equals true thing. So basically, for the last character, we want to update that node to say is_end of sequence for that node is true, because that is obviously the end of a sequence. So let's go to our example really quickly. We are inserting the word any, starting out pointing our current node to the root node, and starting out with the character A. From this empty root node, does there exist another node that it points to for the letter A? The answer is no. There is no node that does that. So what we're going to do is we are going to create that node. It's going to be a new node that will hold the character A. So we're going to create that node, and our root node is going to point to it. And then we created that node right here in this if statement, and then we need to make our current node point there. And then this if statement does not trigger because it's not the end of our word. So then we move on to the next loop. The next character is going to be n. From A, where our current node is pointing to, does a node exist for the character n? The answer is no. So what we're going to do is we have to create that character, create a node for that character for A, set the pointer up. That's what this if statement is going to do, really simply. And then we are going to update current node to point there. And then if statement does not trigger because that's not the last character in the word. So then we move to the next character, which is going to be a y. From current node, which is at n, does a node exist for the character y? Answer is no. We create that node, update current node to point to that. And now this if statement is going to trigger because that was the last character in the word. And basically all we need to do is update this to say true. The node is going to say true. So all the time we were defaulting to false, but this is going to say true. This is the end of a sequence, a valid sequence. And so that's it. We inserted the word any into our try. So now let's change colors and let's insert the word and into our try. So we are once again going to start from the top of this function. We are going to have current node point to the root, and we are going to start out with this character A in our for loop. So from this current node, do we have a node from current node for the character A? The answer is yes, it exists right here. So now this, for the first time, this else statement triggers, and basically we get a copy to that next node and make current node point to that. So we are not creating a new node. We're just going to update the current node pointer to point to the existing A node. And this if statement does not trigger because it's not the end of our word. Next, we are going to look for this character n, and from this A, this is our current node, does a node exist for the character n? The answer is yes, it exists right here. So this else statement triggers, we update current node to point to that existing one, and then this if statement triggers this time. So this node is, sorry, let me rephrase that. This character n is the last character in the node, and so what we need to do is we need to update this false to be true. This is the end of a sequence. So this is what so we finished the insertion, and this is what our try looks like right now. We've got our empty node, and we've got this sequence right here, and we've got true right here for this node because it's the end of a sequence, and true right here because it's the end of a sequence. And this is what our try looks like. So that's basically what the insert looks like. the pseudocode actually is kind of hard to code, but when you go through the operations with our picture, it's really easy. It's not too bad. You just create a new node if it doesn't exist. And if it does exist, you get a copy to that. And then all you need to do is update that Boolean is end of sequence anytime we hit the last character. So that's insertion, super simple. And now we need to look at the contains. So the next operation we want to look at is checking if a character is contained in our trie. If our trie has this character, if it was inserted before. So for our example, I'm going to switch colors right here. We're going to check if our trie contains ban and if our trie contains the word an. And you know what? Let's do the word a too. So we're going to check three things: ban, a, and an. Those three words we're going to check if our trie contains it. So I'm going to switch colors. Let's do a quick overview of what the pseudocode does. It's going to be basically the exact same as before. We've got a function named contains, and it returns a Boolean, true or false, if the trie contains this, and we pass in a string that is going to be the word. And so we've got the two things going on again. We've got one pointer to a trie node that is going to be iterating through our trie. And then we've got this for loop that is going to be iterating through the word that got passed in. Two things going on at the same time, but it's not too bad. Same exact thing as before. We are going to check if a node exists for the character that we're checking. If it doesn't exist, then we return false immediately. You know, we'll see that in the first example. We know that the word wasn't inserted if the node doesn't exist. Otherwise, we just have to update our current node to point to the existing node. And then we do our little trigger check here. Our if statement, if it's the last character in the word, then we have to make sure is end of sequence is true. And if it is true, then we return true. Otherwise, we're going to have to return false because it wasn't inserted. We're going to go through each one of these right now. So 3 words. First word is ban. So using this green marker, our current node is going to point to the root. That's what this starts out with. We are going to look at the first character in the word, which is B. So from this current node, does a node exist for the character B? The answer is no. All we have is this A right here. This character doesn't exist. So right now, this if statement triggers the next node for B does not exist. It's false. So we return false immediately. This failed. There's no word ban in our trie. Let's switch colors to red and look at the next word. So once again, start of this trie, we are starting out current node at the root, and the first character is going to be an A for our for loop. So from the empty root node, does a node exist for the character A? Answer is yes, right here. So this else statement triggers. We update our current node pointer to point to that node. And then what this if statement is going to trigger. So this character A is the last character in the word. But is the current node end of sequence true? The answer is no, it's false. It's kind of hard to see, but it's false right here. It was never inserted. So we have to return false basically down here. We stop and we return false. It doesn't return true because its end of sequence is false. So this fails. This is a false. A does not exist in our trie. So finally, let's do one more color. This is going to be the last example. Let's switch to this gray right here. So start at the top of the function. We are checking for the word an. Current node is going to point to the root node. For loop is going to start out at this letter A. From the root node, does a node exist for A? Yes. Update current node to point to that in this else statement. This if statement doesn't trigger, so move on. Current node points to this. Move on to this character. Does a node exist for N from this character, this current node A? The answer is yes. So we will move current node to point to there. And this is the end of the word. This character is the last character in the word, true. And then is end of sequence for current node is true? Yes, it's true right here and it's blue. So we return true, yes. And was inserted into our trie. So that's basically it. You can see basically all of the 3 things that we have to go through. In total, there's like 5 edge cases, 5 actual things that we have to go through, and we went through each one of those. Pseudocode's not that bad. So that's basically the operations that you need to perform on a trie. We initialized, we did the insert, and we did the contains. And then there's this other operation here that I'm not going to go through. the operation is basically the same as contains, so you can go through the code yourself if you want to do that. Let's look at the code that's on GitHub that I have cloned locally really quickly. It's a C++ project. You can see our main function, our main file will initialize the trie. We're importing it from trie.hpp. We'll go through that in a second. Initialize the trie, insert apple, banana, and apricot, and then we just assert that our trie does contain apple. It does not contain the word app, and it does contain the word apricot. Then we test out the contains method, and then we test out this prefix exists method, and that's it. So let's just make sure that this code compiles. That's how you work. That's how I structure most of my projects. Yes, it does compile, so yes. Let's just look at a high level what this looks like, because this is like object-oriented design right now. So we are importing the hash map library, unordered map in C++. This is basically what our trie library looks like. It's a class. It's got two private things going on here. One is a structure for a node. That's basically what our trie node is. One is a pointer to a node, which is going to be our root. That's all we need to set this up. Then we've got a constructor, a destructor, the insert operation, the contains operation, and the prefix exists operation. We sort of went through this, so no need to spend too much time on that. So our node is going to have a character C. It's going to have that Boolean is end of word, is end of sequence. And then we've got our hash map right here. I've got two constructors here that the false is end of word to false if we don't pass anything in. And we say that if you pass in a character, then the node is going to set char C equals that new char that you pass in. Basic object-oriented design. The constructor for the trie, when we initialize the trie, we initialize the root to be an empty node. And then the destructor I did not do. Maybe I'll code it out later. But it's important in C++. If you use a new keyword, then you must delete the allocated object when you destruct the object, otherwise you'll have a memory leak. So realistically in C++ we should have used a share pointer. We should not have used the new keyword, but I just wanted to make the example as simple as possible. So there is a memory leak right now. So this is the insert operation. It's basically the exact same as a pseudocode, which is great. The only difference is checking if the next node exists. You have to use a little bit of special syntax to work with the hash map in C++, the unordered map. I've got this ternary here that just sets this next node. If it does not exist, then we create the new node, and if it does exist, you use the one that we found in this previous find operation. That's basically it. So the contains method basically uses the exact same type of code. It's really nice. So for a trie, when you need to iterate through, it's basically the exact same code every single time. And this looks exactly the same because it's basically the same thing as contains. You can go through this one if you want. The only difference is instead of checking if end of sequence is true, when you're checking if a prefix exists, all you have to do is check if the node exists. You don't have to worry about if it's actually the end of a valid sequence. That's all that is. So back here, let's end up this video by looking at when you would actually use a trie. There are a couple good use cases when you want to use a trie data structure. One is when you want to autocomplete a word. So you can pass your sequence, whatever your prefix is, into the trie, and then your trie can look down the node path to see if you have any matching words. So for example, do we have any words that start with APP? Well, for like a hash map, you would have to do some like weird stuff, or if you were trying to use a different data structure, it might be super weird. But with our trie APP, we can look down the trie, and then we can just continue down each path, and then we see if is end of sequence is true, then that would be a result you would return to autocomplete, which is really nice. So autocompletion is really great for tries. And then if you ever need to create a dictionary, so that's basically exactly what a trie is. If you need to insert a word, and if you need to check if that word was inserted before, if it actually exists, trie is the best data structure because so memory is great in two ways. Memory is great because overlapping characters share the same character, the same node, and so if you've got a million words that start with the letter A, you don't have to duplicate the letter A every single time for each one of those if you were to use an array or a hash map. The trie data structure is just going to make one of those A nodes. And the other thing is when you actually want to do the contains operation, it's a bit more efficient on memory because it kind of already exists. So that is when you would use a try. If you want to test your knowledge, there's actually a lead code problem that implements the exact same thing that I have set up right here. So if you want to test if you can write this code yourself after watching this video, come to this page. There's a link right here. You can come to this page on lead code and see if you can implement these methods. And these probably do get asked in interviews, so I would recommend checking it out yourself and seeing if you can code it yourself, because it's actually a really good example of data structures and algorithms and object-oriented design. So it's really good. So I'm srcmake. If you like this video, please like it, below, and subscribe and follow on Twitter and everything else. If you want to see something, leave a comment, and good luck on any interviews you have, and try to use this if you can. Anytime you can use a good data structure, it opens your mind on possibilities for other things. So it's really important.